Okay, from now on, we will study how this Faraday's law of induction have an effect on electric circuits. Okay, and in order to study that, we will think about coils. Why? Because coil has many turns of wires, and the effect of induction will become stronger. Okay, so the examples of coils are shown here. For example, here the wire goes in and then make many turns and then come out. So it actually does not exactly form a closed loop. The current can go in from one of the open ends and then come out to the other end. Okay, so we call this device inductor, and this symbol is just like this. Okay, and what is happening in this inductor is that when the current goes in, and of course it will generate magnetic field, strong magnetic field inside, and if this magnetic field is changing, then it will again have an effect on the original current. That's why we are interested in it. Okay, and then we will study it in more detail later. And this effect is actually described in the quantity called the inductance. And it is defined like this. It is defined as the number of turns in the coil multiplied by the generated magnetic field divided by the original size of the current. Okay, so basically what it means is that if the same amount of current produce more magnetic field, then the effect of this induction will be stronger. Okay, that's why we define it this way. And then here we are not going to calculate inductance for many different types of inductors, but instead let me show you the typical example, typical result for ideal solenoid. So if you have an ideal solenoid, its inductance will depend on the area of the coil multiplied by the length of the coil, and also depends on the number of turns per unit length. Okay, so basically the inductance of a coil depends on the shape. Okay, just like the capacitance of a capacitor depended on the shape of the capacitor, like area or the distance between the conducting plates, right? Okay, and then we have to think about the unit of this inductance. So it was defined to be the magnetic flux divided by the current. So therefore, it will be Tesla meter square divided by the area, and then we will give it a new symbol H, and then we call it Henry. And of course, this Henry also comes from the name of a scientist. Okay. And then finally, I will explain how this coil or inductor has an effect on the electric circuit. Okay, and this phenomenon, we call it self-induction. Why self-induction? Because in this case, we are not giving any magnetic field from outside. We are not applying any magnetic flux. If there is any current, then it will create the magnetic field, and then if this magnetic field is changing, it will have an effect on the original current itself, just like what we have said in this sentence. So therefore, this current have an effect on itself. So therefore, we call it self-induction. Okay, and let me explain it. So here, suppose you have a conducting wire connected to this coil, and then the current is going in from this direction. You know, whenever you have any currents, there will be a magnetic field inside this coil. But now suppose it's increasing. If the amount of if the amount of current is increasing, then the amount of or the size of magnetic field will also be increasing, and it's changing, right? So the change in magnetic flux will induce current, and then according to the Lenz's law, if there is any change, nature wants to oppose the change, right? So therefore, in order to oppose the increase in this current, now new induced current has to be flowing in this direction. Okay, It's just like having a battery this way, so that the potential will go up along this direction. Okay? So now let's try to use mathematics to describe it. Now what we are doing is first we get the definition of this induced definition of the inductance and simply rewrite it so that the N phi b is equal to Li. And then we get the original form of the Faraday's law, which tells us that the induced EMF is negative of the time derivative of the magnetic flux multiplied by the number of turns. Okay, and then this quantity is actually here, so you replace it by Li. And then we know that this inductance is simply a constant. It depends only the shape, depends only on the shape of the inductor, so therefore it does not change with time. So therefore we write it this way finally. So what it tells us is that if the change in current is very large, then there will be larger induced EMF, and of course if the inductance is large, then there will be a large induced EMF, right? Okay. And where does this negative sign come from? Of course, it comes from the Lenz's law. Okay. And then let's see whether it makes sense or not. In this figure, now the current was increasing, right? Current increasing means that the time derivative of this current will be positive, right? And then L is always positive. So therefore, which means that now V int is negative. What does it actually mean? If you follow the direction of this current and then go around here, now we come across this battery, which we considered to think about this induced current. And then when you, according to what we have learned previously, if you go from positive to negative terminal of the this EMF device, then potential has to decrease, negative, right? That is why we have negative. So it makes sense, right? Okay. Then how about a different case of the same current actually decreasing? If it's decreasing, it means that di divided by dt is actually negative, right? It's smaller than 0. And then if it's decreasing, now nature wants to oppose the change, so it has to create an induced EMF going that direction in order to compensate for the decrease. And for this to go this direction, it's just like having a battery this way, right? So then if you move from the negative to positive terminal, then this EMF has to be increasing, which means positive. So then how do you get positive value? Because we have the, again, minus L multiplied by this. So if you put it here, it becomes larger than 0, right? Okay, so it makes sense in both cases. So as a result, try to remember this equation, and then we may use this potential difference in the direction of current, whether the current is decreasing or increasing. Okay, it will be very useful later. Okay, in this slide, we will see how the self-induction effect appear in simple circuits. By simple circuits, I mean a circuit including an EMF device and a switch and a resistor and an inductor. We call this RL circuit, the resistor and an inductor. Okay. Previously, we studied this RC circuit, right? So here we had the resistor and a capacitor instead of the inductor. Okay. Well, what you have studied in RC circuit is very closely related to what we are going to study here. So I strongly recommend you to go back and then make a review. Okay. Anyway, so here in this circuit, in the beginning, the circuit is open. So therefore, the current I will be 0. Okay. And then what's going to happen if you turn the switch on to A? Of course, if you turn the switch on, the current will start to flow out from the EMF device. But then we learned that this inductor does not like changes in current. So it, according to the self-induction effect, it will oppose the change in the current. So therefore, when the current wants to increase from 0 to certain value, if the change is large, then there will be a stronger opposition from this inductor. So therefore, the current cannot increase quickly from 0, but it will only do so very slowly. Okay, that's what we are going to study. Okay, so during this process, now we want to calculate the time dependence of the current. Okay, how do we calculate the current? Of course, let's use the loop rule. Okay, so going around this loop clockwise, starting from this position, you first come across this EMF device. So therefore, the potential difference is plus V EMF. And then next, you come across this resistor. Along the direction of the current, it has to be a minus IR, right? Okay. And then you come across this then you come across this inductor. And then along the direction of the current, what kind of potential difference there will be? Of course, if you go back one slide, there is an equation that is conveniently used. We just learned that if you go along the direction of the current across the inductor, now delta V int was minus of L di dt. Okay, so it is important that you have minus, and this equation can be used along the direction of the current, regardless of the fact that current is either increasing or decreasing. Okay, so from this equation we can get the value of I, but then this type of equation, including the differential form, is called the differential equation. Okay, and this is exactly what we have seen in the case of RC circuit, and in there there was a this differential equation for the charge Q. Okay, and then compare this differential equation and that differential equation. They look similar, right? There are some other differences in the constant, but they look very similar. And this was the solution time dependence of the charge in the case of RC circuit. So therefore, the solution in the case of RL circuit for the current has to look similar. Okay, and we are not going too much in detail, but this is the solution we get. Okay, let's try to see whether it makes sense or not. In the beginning, the current has to be 0. So therefore, if you insert t equals 0 here, then exponential of 0 is 1. So therefore, 1 minus 1 is 0. So therefore, when t equals 0, current is 0. It makes sense. Correct. Okay. And then how about after a long time, after the switch was on? After a long time, very long time, the change will be almost gone. So if the current is constant, then the self-induction will be, there will be no self-induction. So therefore, after a very long time, this inductor is nothing more than a conducting wire. Okay, so in this circuit, if you remove, for example, this part, then the only thing you have is an EMF device and a resistor. So therefore, the amount of current in that situation will be V EMF divided by R, right? So if you insert t equals infinity here, then exponential of minus infinity is just 0, right? So if exponential becomes 0, then current is V EMF divided by R, right? Correct. So therefore, this solution actually satisfies these so-called boundary conditions that we need. Okay, and then this solution and that solution look very similar because both of them are 1 minus exponential of minus t multiplied by something, right? Okay, and then you can also draw the graph of this current as a function of time, and then it will look like it. It starts from 0, and then it cannot immediately jump, so it has to increase gradually, and then finally it approaches the value which is supposed to be the saturation value without the case of inductor. Okay, and then here actually let's try to see this part. This part includes minus t multiplied by r divided by l. So if you define this L divided by R to be some constant, this constant will have the same dimension as the time, so therefore you can rewrite it this way. So what it means is that if this time constant is very large, then it will take long time to become saturated, right? And this time constant, which is called the inductive time constant, is proportional to the inductance and inversely proportional to the resistance. Why? If the inductance is large, then opposition will be stronger, so therefore the change will happen very, very slowly. That is why the time becomes longer. And how about the case of large resistance? If you have a large resistance, then the final goal of the current is very small. So if the goal is small, then it doesn't take long time to make the full change. That is why it's given this way. So, and then this capacitive time constant we studied this in the case of RC circuit. Okay, so try to compare these two and you get the idea of what's the difference and what's similarity. Okay.